All right, well, thank you all for coming. It's my pleasure to introduce Ben Althouse, who is visiting us from the Institute for Disease Modeling, which is, as you might guess from the name, a disease modeling institute in Seattle that's funded by Bill Gates and the Gates Foundation. Ben did his master's and PhD in statistics and epidemiology at Johns Hopkins, and then he did a postdoc at Santa Fe where he held an Omidyar Fellowship, which is how I know Ben. And then from there he went to Institute for Disease Modeling. He also has affiliate appointments at New Mexico State and University of Washington. As you can see from his CV, he's worked on a wide variety of topics, but mostly structured around infectious disease transmission and diseases like Zika, Ebola, Dengue, and a lot of work on sylvatic, so transmission in animal reservoirs, in particular primates. And today he's going to talk about work that he's been doing over the last year or so on modeling Zika virus transmission.
Thank you, Sam. Thank you, everyone, for coming, and thank you for inviting me. It's been wonderful being here this past week. So as Sam said, I worked on a bunch of different things. This is coming out of some thesis work that I did years ago, actually, on Zika. It's been a strong collaboration with individuals at University of Texas Medical Branch and New Mexico State. This is going to be the first half of the talk. And then the second half of the talk, thinking about sexual transmission, is work with Sam, Antoine Allard, who's in Spain, and Laurent Hébert-Dufresne, who's moved to Vermont. So what are we talking about? We're talking about this disgusting blob here on the screen. It's something that is across the globe. It spreads from Africa to Asia to South America. It makes people sick, maybe. It gives them rash, hives, conjunctivitis, gives them fevers, cause devastating effects to infants. And it is transmitted amongst people who have very different contact patterns. So for example, this is an individual who was a flight attendant and went on 2 flights, and so he or she contacted 342 people and 300 people in one day, and then 15 family members. This is a grandpa who went to a family reunion and only contacted his family. Each of these individuals, of course, has a different immune profile. So some may have been affected early on with a related virus or bacteria, and they've played through their life course amassing infections. Of course, each of these individuals is driven by behavior. Freud, economics. If I'm sick, but I can't afford to stay home, I go to work. I have the potential to transmit. Additionally, what we're talking about, this virus may be spread through multiple forms. We have to deal with transmission dynamics not only in a human, but also in mosquitoes, say. And perhaps it's transmitted in more than one way. So not only mosquitoes, but it could be transmitted sexually. And of course, there are always things we can't control for, happens all the time. And of course, everything is working under the guise of evolution. And so what happens is all of these things come together to create a complex system, which I'm sure you all know and love very well. And so to understand the dynamics of something that comes together as more than the sum of its parts, we need this. What is this? What? No, it's not a pipe, right? It's a model of a pipe. And it's a pretty good model, but it's not an actual pipe. And so to understand this, we need a model to figure out the transmission dynamics. Okay. So that's the intro to how I go about thinking about these problems and what we all do. Today we're going to talk about 2 things. As Sam mentioned, the risk of a sylvatic cycle. So what's the probability that we're going to maintain Zika in non-human primates? And then we're going to talk about sexual transmission, which is a pretty hot topic. We've recently finished some work, and in fact I'll have some results at the very end of the talk that I did this morning. So please critique. Okay, so the first question is, what's the likelihood of establishing a sylvatic cycle in South America? So we're interested in this because Zika came from the Ugandan forest out of a sylvatic cycle, Middle Africa in the late 40s. It then bounced to Southeast Asia, as well as to Africa, and I think this happened twice, 2 separate introductions, so you have multiple lineages circulating. And then from Southeast Asia, recent work has shown that it's moved to South America and across South America here. And so what do we need to know to really answer this question? Well, what is a sylvatic cycle? Okay, simple enough. Why do we think it's possible? Is this a valid question that we should be going after? once we've decided that, what is the probability of establishment? We're going to build some models to try and answer that, give an estimate of the uncertainty. What else do we need to know? So we can build a great model, but there's going to be a ton that we have left uncovered, and so we'll go over that. And then what would be the consequences of this? So first of all, what's a sylvatic cycle? Sam already went into it. We'll start with the human cycle or the urban cycle, where these viruses, dengue, yellow fever, chikungunya, are maintained in humans that live in cities. They have vectors that prefer to feed on humans. Aedes albopictus, Aedes aegypti, and it's maintained. So this is Rio de Janeiro, this is Dakar, Senegal. These are Bangkok, cities that maintain the virus within humans. We're talking about today sylvatic cycles, so cycles of these same viruses in non-human primates, potentially other mammals, with different vectors who may prefer to feed on these other animals, and so it can be completely maintained. And why it becomes important is this middle. So if you're in a rural area and you either work or live next to a forest and are constantly getting exposed to these viruses, but then go to Dakar and hop on an airplane, it can spread that virus worldwide. So that's what we're interested in, and that's why it's important, and why we've put time and energy into thinking about it. So as I said, my thesis work spent a lot of time thinking about sylvatic cycles in Dakar, or in southeastern Senegal. So this is Senegal, here's Dakar, the capital. We're talking about Kédougou down here. And so the Institut Pasteur has been routinely collecting data for now 60 years. Same way. They go to these platforms and they roll up their pant legs and they wait for a mosquito to land and they capture the tube. They wait for a mosquito to land and they capture the tube. They've done it the same way, same places for 60 years. They look for mosquito virus isolation, so not just PCR, but they actually try and grow some viruses to think of transmission risk. They've, until I started on the study, they were only opportunistically capturing primates, so if a primate happened to cross by the study or they captured it or whatever, they tested it and they have some viral isolations from primates. And then in 2010 and 2012, right when we were starting to work on this project, they upped it. So they systematically opened up the mosquito sampling sites and they started collecting primates in this more systematic way. So these are the data. As I said, 60 years. They tested these 4 major viruses, dengue, yellow fever, chikungunya, and Zika. Each of these blue is an isolation from a mosquito pool, and we can count the number of positive pools. Darker blue, more counts. And there are a few things to note. One is differences in periodicities. So this is the Fourier spectrum, which tells the dominant periodicity. Dengue, it's about every 8 years. Yellow fever, 6. And chikungunya and Zika are about 4. Here's focusing on Zika. What's kind of striking about this to me is that it's almost every year. You see a lot of Zika here. These furcifer are very much sylvatic vectors. They like to feed on non-human primates, stay in the forest, but they do bite humans. But we see a lot of it across the study period. And of course, it was only here when it started to branch out and, don't have the data, but 2015, now it's something. Clear evidence for a sylvatic cycle in Africa. In 2011, there was actually an outbreak in the study. We actually captured it in the study. We got it from 10 different species of Aedes, as well as we saw it in some primates. So it was previously isolated in Cisavius and Patas monkey. This is ongoing work. So why do we think now that since it's established in Africa, why would it establish in South America? We know old world primates and mosquitoes are able to sustain, and both of these hosts are available in South America. They're there in South America. Additionally, we know for a fact that yellow fever has established itself in a sylvatic cycle. So if we look in southeastern Sao Paulo, this was an outbreak that happened a couple of years ago. Lots of cases coming directly from the forest. So again, individuals either working or living very close to the forest, and it's devastating. Without vaccination, 50% mortality.
Yeah, you're talking about monkeys or humans?
Humans.
Humans.
Humans, yeah. That's a good point. So yellow fever actually affects monkeys similar to humans. So they identify both dead monkeys and humans in these places. So we've established what a cycle is. We've established that it's an important question because once it's there, it may persist. We have vectors in South America that maintain it. What is the probability of establishment? So to answer this question, we built a simple, relatively simple stochastic transmission model, a Gillespie type model. So it's a well-mixed population, but it has chances for stochastic extinction. We parameterize it thinking it's similar in transmission dynamics to dengue, which is where we all started. We do a single infectious introduction, so we want to be as conservative as possible. We took the idea that we dropped a single infectious monkey into this population and let it go, and no additional importations from there. To get the probability, we do this over and over and over again because it's stochastic, and we count the number of times that it does not go extinct, and that's our probability of establishment. And we're going to focus on two key parameters. One is the birth rate. So how quickly do these primates reproduce and create more susceptible primates that can then be infected? And then the force of infection. Of course, low force of infection, it may be much harder if my per bite transmission probability is low than if it was very high. This is a little schematic of the model. Mosquitoes are born, they bite infectious primates and become infected, and then they die. We have similarly primates, born susceptible, get bitten by a mosquito, become infected, and they recover. We assume just some basic death rate. We assume Zika actually doesn't do much to these primates, which is similar to dengue, not yellow fever, but they don't seem to have really any disease. And this is an example trajectory. So we start with our introduction, we have some wild initial burst, and then it either establishes or it goes extinct. So a lot of them shoots through susceptibles and goes pow and is gone. And since we don't have reintroduction, it's gone forever. Or it's a big enough population to sustain. Okay? Here's the results of several 100,000 simulations. We'll go through slowly, a little bit complicated. We'll focus down here. So on the X, we have number of mosquitoes in thousands. On the Y, we have numbers of primates in thousands, and we have a primate that turns over roughly once every 25 years. This is maybe a larger primate, and one that turns out lifespan of 15 years. So this has a lower birth rate, this is a higher birth rate, and across two different forces of infection. So this one's 0.15, roughly the per bite probability of transmission. This is 0.3. And we see a lot of blue. Blue is 0 probability, so all of the simulations, or most of them, went to 0. So we seem okay. So if we're dealing with primates that turn over slowly and we have low forces of infection, we're okay. But if we now look up here, it gets a little bit more pessimistic. So across this top row, this is now a primate with a lifespan of 5 years, pretty rapidly reproducing. You don't need super high force of infection or large numbers of primates to maintain. Perhaps a few thousand primates with a few thousand mosquitoes may maintain this. So, as I said, higher birth rate, you're turning over more rapidly, you have a higher probability of establishing. And you do need more mosquitoes than primates. So if you look at these, there's these diagonals, you need generally more mosquitoes than you need primates to maintain. But what else do we need to know? As I said, this is a pretty simple model. There's a lot in here that we need to investigate. The first is, we don't know a lot of the primates, their susceptibility to Zika, specifically viremia. So if you're a primate and I get bitten but I don't mount viremic response, another mosquito that feeds on me is not going to get virus. So it wouldn't be transmitting. The second is susceptibility of other small mammals. So it may be that it's not just non-human primates that are maintaining. There may be other small mammals, bats, squirrels. There's some evidence that dengue can infect smaller mammals, but we just don't know. We need to look a little bit more. The point being, if you have these really small animals that turn over all the time, have multiple litters per year, it's a lot of susceptibles to maintain Zika transmission. If you think about mosquitoes, there may be other mosquitoes that we haven't really investigated as vectors for Zika. Xylophes or Himagus transmit yellow fever, they may also transmit Zika. And so if you have these mosquitoes in the forest and we haven't investigated them fully, they can maintain, or not. The ranges of these hosts and vectors, It's important to assess risk for humans. And then it'd be really nice to know if and the extent of a sylvatic dengue cycle. Dengue has been in South America for years and years. It's likely in a sylvatic cycle, but we just haven't looked, so we don't know. It'd be nice to know, to isolate some of these primates. And we're gearing up a study now that's actually going to set up some sylvatic mosquito isolations so we can look for virus as well as type of blood else to know what they're doing. Consequences, already touched on it. If Zika establishes in non-human primates, it will be there forever. Regardless of whether we get a good vaccine, you can't vaccinate every primate, so it'll always be a constant force of infection like yellow fever. Have to keep vaccination rates up. And you really need good surveillance, because if you had a pocket of unvaccinated individuals when everyone else is surrounded and sylvatic Zika comes in, it could wreak some havoc. Any questions before we go on to sexual transmission? Yeah.
Yes, so if you go back to the to your simulation for the list model, so when you calculate this diagram, obviously a number of simulation dies. But now, from my knowledge, if you run enough long this simulation, they all will die.
So
This is a stochastic absorbing system. Sooner or later, if you wait enough, will die.
So we're pumping new susceptibles in all the time.
Even if you just an SIS, imagine an SIS. Even an SIS, the stochastically it dies out. So you have always the probability of survival for a certain time duration goes down like an exponential function. And it depends on the size. The larger the size of the population, the smaller is the probability that you die out. In a sense. How you calculate here the survival probability? So I wanted to have say some more details about this, because this might be something that is finite size dependent.
Yeah. So I mean, it's definitely dependent on population size. So if you have lots of primates, lots of mosquitoes, you have lots of simulations that persist. We stopped the simulation, I think, after 5 years. So we didn't run it out for hundreds and hundreds of years. We stopped it saying, in the next few years, what's the risk of establishing?
So this is 5 years is your cutoff. Everything that was survived until 5 years.
Yeah.
And everything that dies out before.
Yep.
Yeah.
Yeah. So we basically take that snapshot of 5 years and say who died and who didn't.
And you did any kind of distribution of the survival time? So if there is really a kind of discontinuity, everything dies out?
No, that'd be interesting. No, we didn't. No, we were interested in the actual question: what's the probability of establishing in 5 years? Short time periods. What's our risk? But we should talk more. There's probably an analytical way to do it, but I didn't do it. Great. So, what are we talking about? Just to come back, we're talking about Zika virus. It's a flavivirus, like dengue. It's transmitted by mosquitoes, predominantly Aedes aegypti and albopictus in human populations, like dengue. It's maintained in sylvatic cycles in Africa, like dengue, and has had explosive outbreaks in Southeast Asia and South America, like dengue, and usually causes no symptoms. Maybe fever, myalgia, rash, like dengue. So, we think that this virus behaves a lot like dengue. So the outbreak started in mid-2014 in Brazil. All the previous work, the couple hundred papers that have been published up to that point led no reason to believe it would be any different from a dengue epidemic. And in fact, 80% of Zika is asymptomatic, so perhaps it'll even be better than dengue. There's no evidence for hemorrhagic fevers, which you get in a second or a third dengue infection or a second infection. But we all know what happened, right? These reports coming out of Northeast Brazil of babies born with microcephaly led us to believe, well, maybe something is different about this. And so after science came around, it was, came out that Zika virus causes microcephaly and other neurological defects. So we call it surprising fact number 1. So, okay, Zika causes birth defects. That's terrible. It might be more of a public health emergency than we have thought before. So it's causes birth defects. Maybe it's spread sexually. There was one anecdotal paper, I'm sure you've all seen it, where this guy, Brian Foy, went to Kédougou in Senegal, incidentally where we were working, came back to Colorado, and his wife came down with Zika 2 weeks later. And so they wrote this paper saying probable non-vector borne transmission of Zika in Colorado. And so I saw this when it came out. I've been thinking about Zika at the time, and I was thinking, there's no way. No other flavivirus is transmitted sexually. It's not common, but they do have vectors that can spread it in Colorado, and the timing is such that he could have gotten into a mosquito and then into his wife. Nothing, no big deal. Of course, what happened? See persisting in semen, evidence of sexual transmission, and so we lead to surprising fact number 2: Zika virus is transmitted sexually readily and persists in semen for a while. I'll get into what that means in a bit. So, second half of this talk, we're going to talk about sexual transmission, which is something, as I said, unique to this flavivirus. So we've got lots now of documented transmission. It's no longer idiosyncratic. It seems pretty well done. Male to female, male to male, and then actually female to male as well. And I said it persists in semen for a while. It's been documented in RNA at least up to 180 days, whereas in women it could be less than 20, 2 weeks, 20 days. So on one hand, you've got ready transmission, and males seem to persist a lot longer. We asked the question, can we maintain Zika virus in a sexually transmitted cycle by itself without the vector? So some previous work had come along. A guy who spells my last name wrong, as well as a few others, and basically they made the argument that the per chance probability of Zika virus transmission is quite low. Even with a long duration of shedding, you still would not hit R naught greater than 1. You'd have to have, they argued, Zika virus in semen for 3.5 years at 5% transmission probability to maintain. So we all know what the basic reproductive number is. It's the number of secondary infections. It's measles, and you guys were all susceptible, and I had it. I'd probably infect all of you or most of you. All the way down to MERS, where you infect less than 1. And so they're arguing that Zika is here. But this is missing one clear fact, and I think everyone in the room knows what it is, because we all study networks. Your friends have more friends than you do. The idea being, if I'm infected sexually, I'm necessarily at higher risk than someone who is not having sex, which is not the same with the vector, but it's unique to sexually transmitted infections. That's what I just said. So we set about studying a system with strong asymmetry between male and female, and trying to look at some of these effects of your friends having more friends than you are. So this is an example. This was the original argument. You get vector transmission, maybe some sexual transmission, but very, very little. So your R naught is much less than 1. We don't have to worry about sex. Very few transmission. I will note, this will come up later, women can both now be infected sexually as well as by vectors. Just keep that in the back of your mind. But let's say you hop into another population with completely different risk groups, say MSM, and it spreads like wildfire. You have multiple partners, and you shed for 6 months, so maybe, and so you can ignite these epidemics in subpopulations. And so here's an MSM who got infected by a mosquito, only spread to 1. There may be a monogamous relationship with this guy, infected him, and then just spread. And in this case, the R naught is much greater than 1, because it's spread, and it goes on. And so you have to take both together to come up with accurate estimates for how well this is going to spread. And so we do this. We've all looked at these thresholds. What's interesting about this system is we actually see 2 thresholds. The first looks more classic, where you hit MSM. So this is difference in transmissibility between males and females. You come up to some transmissibility, you get a threshold of MSM. You need a much more transmission in the entire population to then see it. So you see this bending phase transition. So now we can vary that form of asymmetry. So this was pretty high asymmetry. This is weak asymmetry. And this will look pretty familiar. Phase transition, you hit some critical threshold and you see it in the entire population. These are the average size of the small subcritical outbreaks. But now if you extend that asymmetry, you start to see this double phase. So You start here, you start to come up, and as you increase your transmissibility, because you start the MSM and expand to the whole population, you start spreading out. What do some of these networks look like? Of course, this is the MSM network that I showed earlier. This is MSM that now spread through, say, bisexual individuals to women as well. So you have lots of MSM transmission, but also some to women. And so the point of this is we're going to underestimate R naught, the probability of these epidemics, if we don't account for this asymmetry in sexual transmission. Why is this important? This kind of busy plot. This is overall prevalence. This is R naught in a whole population, considering R naught small vector and sexual. This is just sexual transmission, and this is the MSM across rates of transmissibility. This is just a parameter that we can change. And we're interested in R naught equals 1, right? If it's below that, it dies out. If it's above it, it maintains. So, okay, we look at 1, we come across here, and we look at the overall R naught. So taking into account a little bit of vector as well as sexual transmission, we need a transmission probability of over 0.35. Okay, maybe we're okay, maybe we won't hit that. But if you go back and look at the MSM R naught, the critical point is about 3%, so 10-fold difference. If you don't take into account the asymmetry in this potential for establishing MSM. So, by ignoring this friends of more friends than you do, you totally underestimate your R naught and your risk of establishment. And what happens is MSM are typically not targeted for surveillance. Unless they go abroad, they have symptoms, they may be tested, but they typically don't have children, which is the large group that is tested. So you may have this ongoing lingering epidemic that you just won't detect. And especially if 80% or more of the people who become infected are asymptomatic, you can just miss it. And then more importantly, well, not more importantly, but also importantly, there's growing evidence that actually having Zika virus may damage the testes, testicular atrophy as well as others. So there may be direct harm to men as well. So Zika is funny, right? So a lot of the transmission dynamics seem very similar to dengue, but it's got this strong sexual component, and we're going to make the argument that perhaps we should be treating this more as an STI, or at least have a strong STI component than just vector transmission. So major prediction, and I told you to keep this in your mind, our model predicts an excess incidence in women. So again, remember that women now can not only be infected through a vector, because everyone's outside, they're getting bitten by the mosquito, but then they can also get infected by men who have sex with them. So basically you get double force of infection, or at least higher than one force of infection. So again, this is one of those double thresholds that we look at. This is the MSM population. This is now the total population, heterosexual total MSM. MSM is a relatively small part of the population. We can break out the heterosexual components into men and women. You see women is greater. You can then fit the ratio, and the slope is less than 1, indicating more incidence, more prevalence in women, as the model shows, as we'd expect conceptually. So here's a prediction that's coming out of our model. Let's then look for some data to test it. So there was a really nice paper, well, a very nice idea. The paper is good. Showing incidence in Rio de Janeiro. And the beauty of this is they broke it down by age and sex. So if you look here, it looks like there's about a 90% increase in incidence, maybe twice incidence in females to males, in those that are sexually active. So if you look at under 15, they're pretty similar. If you look over 65, they're pretty similar. And so you might say, and this is very valid criticism, maybe the women are scared, they seek healthcare differently, they're worried about Zika. And so what they did then is they looked at incidence of dengue. And yeah, there's a little bit more increase in incidence in dengue in women compared to men. And they say, okay, that might be due to Zika. So people are going to the doctor more often because they're worried about getting Zika, they're identifying more dengue. They looked at 2015, where Zika was present, and compared it to 2013, and they see a very similar pattern. So again, excess incidence in women as compared to men, similar between 2015 and 2016. We looked across countries, and the data are not always available. I mean, they exist, but they're not always available online. This is Colombia, so same story. Under 15, the rates are identical. Over 65, the rates are identical, but 2 or 3 times the risk in women as compared to men in prime sexual age. We also looked at Dominican Republic, same story. Under 15, the same. Over 65, the same. Excess risk in women. One other thing, and these are the new results that I came across this morning, because we're going to talk a little bit more about this bias. I looked at the differences in men and women over time. So this is not broken down by age, but this is now by epi week. You look at the incident cases per week, and it appears that the differences between men and women is steady over time. And so to me, to my mind, this is evidence against reactionary visiting of doctors. You'd expect when microcephaly first came out and Zika was new, there'd be a panic. And so lots of people would go and get tested, lots of them would get tested. But that you'd expect to go down over time, maybe. And so that's not what's suggested here. It seems kind of sustained higher risk for women over time. And there's more to digitize, so I'll see what the rest of the story is. These are low numbers of cases in this week, that's what the difference is. But interesting hypothesis. So to be critical, and we've gotten a lot of critical feedback saying this is, this is just due to hysteria. This is just due to women who want to become pregnant, get excess testing. And so we asked, is this sex bias real? And we found a few papers that look at blood donors that screen them. So this is a study from Puerto Rico, and they found huge numbers of cumulative infections, 4,500,000 cumulative infections for the first few months of the epidemic in Puerto Rico. And in fact, they did find a sex bias, but it's the other way around. So, there were twice as many males getting tested as females, but 3 times the risk of Zika in our RNA in the blood, males to females, so it's backwards. We don't know a few things. So we both, Sam and I were looking at that, and we're scratching our head, and we're saying that that's totally against what all of the incidence data show. What's going on here? Well, maybe there's some differences in the duration of virus between men and women. So this was a study of 30 or 40 men, and they looked at persistence of Zika in various fluids. And what we take away from here is at 4 months, 30% of males, anyway, have detectable RNA in their blood. So no symptoms, but I have RNA in my blood. If I'm a man and I go give blood, I'm going to be biased, potentially. This is some evidence from rhesus macaques. Not a huge difference necessarily in the time, but perhaps some differences in the magnitude. So this is the peak RNA between male and female macaques, and the sum. So this is basically the total amount of virus that they shed over this duration, and perhaps a little bit of a difference between men and women. The other thing that we're missing, though, is we don't know the denominators of tests. So if we knew how many tests went in, we could potentially try and control for the male-female bias in blood donations, but it's not reported. And so now we're beating our heads against the wall, trying to contact labs to try and get those denominators. So that's it. Zika as an STI is definitely vector transmitted, but I think the evidence is pointing to ready sexual transmission. This large asymmetry and the fact that you don't take into account that it can be transmitted sexually will upset your estimates of transmissibility, and there are not. We may have persistent dynamics in MSM populations. We have ideas of going into MSM communities, doing case control studies with non-MSM to see if there's an increased risk of, say, antibody prevalence, indicative of more transmission. We have an obvious sex bias in cases. We look across countries, there's 2 to 3 times more reported cases in women than in men. But now we've looked at serology and it appears there's a bias in the other way towards men instead of women. So we need to figure out ways to test this. It's going to involve getting the denominators, it's going to involve doing dynamics in men and women, how long do each group have viremia in their blood, virus in their blood. And so that's where we are. I think it's important to keep going. We don't really know the answer, but definitely worth studying in the meantime. So we come back around, just as this is not a pipe, it's a model of a pipe. This and this is not really Zika, but it at least can help us understand some of the aspects of what's going on. So with that, I'd like to thank Kathy, Hadley, Scott Weaver, and Nikos Misalakis, who are the collaborators in the solvatic transmission work, and then Sam, Antoine Allard, and Laurent Berg-Frame, who are the collaborators on the sexual transmission work. And I'd be happy to take your questions, and thank you for your time. Yeah.
So when you look at the data from Colombia, have you ever checked what's their kind of like health agency's guideline for reporting? Because, for example, for the United States, all pregnant women require to be tested. And then you have like several thousand Zika cases of pregnant women just because of that. And if you compare the imported the cases of Zika, then you have a huge bias towards women. I don't know if somehow you can correct that to see Dengue is comparable to Dengue, this urinary Dengue or not.
Yeah. No, that's absolutely right. So the idea is, if I'm pregnant, I'm going to go to the doctor and he or she is going to test me and I'll have a bias. There'll be a lot more women showing up. The majority of what they report are just suspected cases. So the actual number of confirmed laboratory tests, 5% or less of what you actually see. And so for sure, there's definitely a bias in reporting between women and men, which is shown by the dengue. The question is, how much beyond that is there anything beyond that? And then what's the magnitude difference between male and female?
Right, because if you can find, like the government guideline is saying something that all pregnant women to be tested, you can just kind of like crudely get the number of pregnant women, and then add a reporting rate on top of that, which is probably much higher than the other, and then you can more or less get a correction.
Yeah, so I don't have it for Colombia or Dominican Republic, but that other paper that I showed in Rio de Janeiro did exactly that as well. So they subtracted away the pregnant women, and there was still an excess risk. It went down, I don't remember the number, 50 or 60%, but it was still present.
That's a comment. I think in Colombia, I don't know about the early data. I think the late data is mostly from 2 cohorts, I remember, which are basically just pregnant women. So most of the reporting is just pregnant women. So I think this is one of the things you can try to ask them if, okay, of those cases reported, how many were pregnant women? Because that will really be a proxy of how much this is the health system testing or something else.
Yeah.
My question is, whether you say that more or less there is this couple of papers, the Swiss Althouse and the other guys, that they say that more or less it's they see this kind of transmissibility on the sexual route that is about 0.7, 0.5. If you do a bit of, I understand it's difficult, it's not easy, but if you plug those numbers in your work, you get an estimate of what would be the bias actually, and what would be the imbalance. You didn't give us a number, so what is the imbalance that you expect according to
Right. Well, it's about tenfold. I mean, that was that.
This is tenfold.
Yeah, so I mean, that risk of transmissibility, so that plot we were looking at, overall are not versus MSM are not.
In the sense that there is the transmissibility, but But that means, okay, you have another zero component that is about 0.5, 0.7. The one for the mosquito, we know it's about, it depends on climate, temperature, whatever, it's between 2 and 3, let's say, in places, in regular places where there's organization. So the 0.5 is not a small, very small component. But my question is, if you plug in this 0.5, what is the difference in incidence in men and women that you expect? This is what I didn't really get from your numbers. So
Yeah, so that's,
it's that a few percent, or it's
yeah, it's a few percent, 10% or so. Um,
So this is just because I would say, if you would have a prevalence ratio that is 40%, 50%, I would say that very likely somewhere sooner or later you are to be able to observe. But if your ratio is about 5%, 10%, it will be very, very tough because we will be always, there are so many confounders that
Yeah.
that's my.
So that's, yeah, totally agree. I mean, we can back out from the differences in incidence, differences in the contact rates between women and men, basically. And the estimates that I showed are 90%, 60%. That's probably too high. And so we have to figure out better ways to estimate the difference. Adjusting for over-reporting, adjusting for what the bias is in the blood donation. Why does that bias go the other way? I think we're just on this edge where things can be bad. We just need to figure out if we're correct or not. And that's just more basic science to be done.
The big difference between what people would have found with the other sexual transmission models is they didn't allow for the asymmetry in the infectivity of men versus women, right? And so the bias, the sex bias, is coming from the fact that it's super critical in the population of men who have sex with men, and then you get transmission into the exclusively heterosexual population. And in that population, the women are all basically endpoints of infection because the probability of female to male transmission is maybe 10 times less than male to female. And so as a result of that, in the exclusively heterosexual population, you get this strong asymmetry. But that, of course, depends on the asymmetry in infectivity between men and women, because if that goes away, then the sex bias goes away. And so the key parameter for the size of the sex bias is basically just the ratio of the probability of male to female versus female to male transmission. And depending on the size of that, it can be massive or it can be very tiny. And in the literature, it looks like 70, 80% of, like for macaques where they do the experimental infection, 70, 80% of male to female transmissions, well, 70 to 80% of male to female contacts result in transmission, and maybe 20 to 30% of female to male. So I guess probably another answer would be that parameter is also kind of unknown, and the sex ratio bias is big. The other issue is that if you include individuals in the MSM community, then the sex bias can easily flip in the other direction because the claims in the models that you have a supercritical outbreak in that community. And certainly for the data that we have no information on anybody's.
No, that is
So
I actually won't.
Yeah.
Really.
Yeah. And the blood donation data is complicated because you have to, if you report having symptoms, they won't let you donate blood. And in the Gap Island study where they looked, men were less likely to report having symptoms than women, controlling for the percent that were actually ended up being positive. And so it may be that part of the male bias in the blood testing data is that women are more aware of being infected because they're concerned about the pregnancy risk, and so they're not donating blood or they're reporting the symptoms, and so it very quickly became like a black hole of so many parameters that no one is measuring.
Any other questions? Well, thank you very much.
Thank you.
Yeah.